Hello and welcome to the National Weather Service Seattle, Washington office presentation on frozen precipitation. We may not get much right here in Seattle, but around us, especially up in the mountains to our east and west, there can be some serious snow. It may seem like those little crystals must be formed by magic, but we're here to tell you how they work and what makes them. We'll start with just that. The basics of how snow is made and what conditions have to be present to do so. Then, we'll move on to different types of snow. It comes in all different shapes and sizes, and can be transformed into other types of wintry precipitation, like graupel and hail. And when it's cold outside, we can also get sleet and freezing rain. So why not take a look at what those are and how they happen as well. Let's get started on what's going on up in there in those icy clouds. It may seem easy enough to get frozen precipitation, but actually the process is hard to start. The issue is that pure water actually doesn't like to freeze unless it's colder than -40 degrees, which is obviously very cold. While that temperature can occur high in the clouds, like where the wispy cirrus ones form, it's not enough to get the snow going most of the time. What's really needed to get that water to freeze is something called an ice condensation nucleus. This is a particle in the air that's already shaped similarly to an ice crystal, which the water feels welcome to freeze onto. These are actually not very common, and the most notable are silver iodide, which used to be used in cloud seeding, certain bacteria from leaf decomposition, and, of course, already frozen ice. The good news is that once the ice starts to form, it's a very rapid process because the water tends to prefer being frozen rather than liquid. Depending on the atmospheric conditions when snow is forming, the shape will come out differently. Namely, this depends on how cold the environment is and how much moisture there is. The simplest form of snowflake is the plate shape. It is a tiny, flat, hexagonal piece of ice. They choose this shape because that's the shape of an ice crystal. These tend to form under any temperature when the air is not too moist. If it's more moist, more complicated shapes form. As the plates grow, they take on a new shape. If it's cold and wet enough, they start to grow arms at each of their points. They're now called stellar plates. These arms and patterns on each of the sectors remain remarkably symmetrical as they form. If the air is even a little bit more moist, these stellar plates will continue to grow in the most spectacular way. They will grow more little arms on the points of each of their arms. At this point, the snowflakes are getting fairly large, and now we can easily see them. These are probably the most popular type of snowflake. It's what we envision snowflakes to be, and since they're so light and complex, the snow on the ground is very low density, which is the perfect powder for winter sports. When the air is just a little too cold or warm for dendrites to form, the plates tend to instead evolve into hexagonal prisms, called columns. As these columns grow, they often create hollow cones on their ends. These regions are generally too small to notice, but it is a very interesting phenomenon, especially in its symmetry. These are called hollow columns. If it's sufficiently moist and around just the right fairly warm temperature, these columns will continue to grow until they are very long and skinny. Now they're called needles. Instead of looking like classic snowflakes, they look like little hairs. Sometimes, instead of a column growing out into a needle, the ends will start growing into plates. These are called capped columns. The top picture here is of a capped column from the side, and the other is the same snowflake from above. All the snowflakes that we've talked about so far have been individual ice crystals. But as snowflakes fall, they often can't help but bump into each other. A lot of the time when this happens, the snowflakes stick together, especially if it's fairly warm outside. In a lot of places, the only snow that ever falls is these large, wet clumps of snowflakes, which make especially good snowballs. When snowflakes collide into water droplets instead of ice crystals, they still tend to stick together. This is especially true because the water is between freezing and negative 40 degrees. At this point, we call the liquid water supercooled, and it will freeze on contact with anything. The process of collecting supercooled water is called riming. You can see it in these pictures as little spots all over the snowflakes. As the snowflakes fall, they may rime more and more, until you can't even tell the shape of the original snowflake. This type of precipitation is not commonly talked about, but it is a fairly common occurrence. It's called graupel, grows to about 2 to 5 millimeters, and looks like an opaque, bumpy ball of ice, which falls apart when you touch it. Graupel is often mistaken for small hailstones, but the process is quite different. Hail forms in the middle of a thunderstorm, where the upward winds are strong enough to hold bits of ice in the cloud, cycling them through the thunderstorm repeatedly. As the balls go through the cloud, they collect water, growing bigger. Sometimes you can even see the layers of a hailstone where each new coating of water formed. These hailstones keep getting bigger until they're too large for the winds to hold up, and then they fall down. If you find a hailstone, it will be much more clear than graupel, and will be much too hard to fall apart when you pick it up, more like the ice you find in your freezer. If you find hail that's curiously tiny, it probably isn't hail. We have another type of frozen precipitation falling from our skies, called sleet. This can be a bit confusing of a term internationally, because it means different things depending on where you are, but here in the US, sleet is made of tiny ice pellets. The way that these form is by rain falling into a layer of air that is below freezing. These raindrops freeze into little balls, which fall to the ground. We mentioned before, though, that pure water doesn't freeze until negative 40 degrees. The sleet won't necessarily form even if there is a freezing layer. If it doesn't freeze, we have a much more dangerous form of precipitation on our hands, freezing rain. Freezing rain is a supercooled water that will freeze instantly upon contact with anything. That means everything from tree branches or your car to the road. Each of these examples pose a different problem. If there's an accumulation on a tree branch, it may become very heavy and could easily snap off. A layer of ice on your car makes it so that you can't see out your windows well and might not be able to open your doors. The worst of them all, however, is when it freezes onto the road. This creates a thin layer of ice that is super slick and hard to see, often called black ice. Upon driving on this ice, cars will swerve, causing the cars behind them to brake, which causes those cars to swerve as well, resulting in massive pileups. One of these massive pileups occurred on January 18, 2015. A simple freezing rain event outside of Philadelphia caused hundreds of cars to crash into the car in front of them during the morning commute. 5 were killed in this massive accident. While you can't see it in this fairly low-quality picture, cars that crashed into the semi-truck shown were ripped open like tin cans. This is why you should be extremely careful and only drive if absolutely necessary during a freezing rain event. The same goes for freezing fog, which is similar, a supercooled fog that freezes on contact with anything and everything. On a much lighter note, let's get back to snow, and how it can be made when the atmosphere doesn't provide it. We talked earlier about how stellar dendrites make the best powder, and we can see from this image of artificial snow that it does a poor job of recreating that light snowpack, but skiing mountains do the best that they can. Snow machines do this by spewing water and compressed air. As the air decompresses, it gets colder, and the droplets of water freeze and land on the slopes. This process explains why the structure of artificial snow is nowhere near as complicated as a real snowflake. There's a lot of interesting information in this presentation, but what to really take away is the amazingly complicated variety that wintry precipitation comes in. When we hear about all the minutely different types of frozen precipitation and the variability of snowflakes themselves, we see that even tiny changes in conditions will result in vastly different weather. It's no wonder that schools have so much trouble deciding when to call a snow day. Thanks for listening, and make sure to visit us at www.weather.gov/Seattle for more information and for weather alerts and forecasts in your area.